We are now recording. Let's get the slideshow set from current slide. And amazingly, this morning in my first class, when I brought up PowerPoint, it came up in the right mode. It didn't come up in presenter mode. I thought, nice, but now it's in presenter mode. So the hide presenter view. And then I didn't have to do any of this morning. I don't know what was its problem, but it was a good problem. All right. What? What's that?
It shifted over weird.
Yeah.
It's weird.
Yeah. But it'll be okay. Yeah. Okay. Any questions, anything up till now? Okay, what I think we left off last time was this one. Example 6, page 59, section 2.3. Solve this differential equation. Ooh, let me get my pen. I forgot that. And I have to go with the dark blue because the black would turn it off. Okay. dy dx, your different derivative, plus y is equal to f of x. Okay? It's an initial value problem that y of 0 is equal to 0. And here's the catch on this one. F of x is not a continuous function. It is a piecewise defined function where it's 1 from 0 less than or equal to x, less than or equal to 1, and it's 0 beyond 1, x greater than 1. Now they draw the graph of it over on the side, you see. Do you notice one kind of little picky thing that they did wrong there?
Say that again.
One thing wrong with the graph that they have in the margin there. And it's not a major issue.
That should be an open circle.
No, it is a closed circle up there, but there should be one on the other end because it's 0, it's 1 at x equals 0, not x greater than 0, x, 0 less than or equal to x, not just the way they've drawn it here would be 0 less than x, less than or equal to 1. They should have a little blue dot on the at the 0. Okay, that's just not very important, but it's not going to enter the problem at all, but it seemed like they should draw it right. Okay, so there's your function. Now, how you go about doing this is do two differential equations. Okay, the first of these is dy dx plus y is equal to 1, and this is going to be when 0 less than or equal to x less than or equal to 1. We'll solve that one first, then we'll do the other one. Okay? All right. And then pretty obviously the initial value will only pertain to this one because the other part is not going to pertain at all. Okay. So what do we do here? Say that again then? What's that? Yeah. I wouldn't do that quite yet. Okay? Yeah, I think you have to subtract y first. You're doing what I was going to recommend. I think we can do this in separation of variables, and that would be dy dx is equal to 1 minus y, and then divide both sides by 1 minus y, and put it in differential form. Wait, I got the talking and wasn't paying attention to what I was writing. Okay, divide by 1 minus y, and put it in differential form, which is dy over 1 minus y is equal to dx. Okay. Now that's not how they're suggesting to it, I don't think, but that's how I think I would proceed with this one. Now, the only drawback to this is your y, which y can't equal 1, obviously, okay? And we don't know that y is ever equal to 1, but if it is, this doesn't work, okay? So let's proceed with this. What would you do now? Integrate both sides, and what do this give you?
After log,
Okay.
1 minus y, or you're going to do 1 plus y, or negative 1.
Okay.
I can get a negative.
Okay. Because if you did the derivative of this, you get 1 over 1 minus y, chain rule after minus. Okay. Which you can also write as log of 1 minus y to the minus 1. And this is equal to x plus c. Let's put our plus c in there. And now we are going to plug in your values. Okay? Let's see. Or, let's take e of both sides. I think I would do that. So that would be e, okay? So this would give you absolute value of 1 minus y to the minus 1 equal, and I'm going to rewrite that as c e to the x. Okay? Not the same c. Call this one c1. Okay? That would be e to the x times e to the c. It's e to the c1. E to the c1 is just a constant. Call it c. Okay. Now, that would be 1 over 1 minus y. I'll hang on to absolute values for just a minute. Equal c e to the x. Let's multiply both sides. Basically reciprocate both sides. 1 minus y is equal to c e to the minus x. Maybe a different c now, but it's fine. You know, just reversing. And then let's say add a y to both sides and subtract the other. So that would come out being y is equal to 1 minus c e to the minus x. I mean, I threw away the absolute value signs at some point there. Okay. I think that gives us what it is, and that's where we should plug in y, x equals 0, and y is equal to 0. So 0 is equal to 1 minus c, right? Because when x is 0, e to the minus x is 1. So that means that c is equal to 1. All right, so our equation, our function is now y is equal to 1 minus e to the minus x. Yuck, why did you do that? Okay. All right. Let's see if that's what they got.
And that's good for,
Oh, that's good for the top half. Okay. We still got to do the bottom half. And you see they do get y is equal to 1 minus e to the minus x. Okay. That's good for x's. See, I wrote it there for a reason, right? Dumb luck. Okay.
so to plug it in for the bottom
Right.
part of piece one, we just
Right. So what I'm going to do now is do some erasing.
Y equals 0.
I could have left that, but let me erase all this so nothing gets confused.
So we just kind of pick a variable that fits in that part of the piecewise defined function. Find what C is.
Okay, do it just a second. Let me get this done. Okay. I know what I'm tempted to say, but I want to do the problem for. Okay, the second one is this is equal to 0, and this is when x is greater than 1. Okay? So how would you proceed here? Basically, same way, subtract y from both sides, and you get dy dx is equal to minus y. Divide both sides by minus y, and write it in differential form. Very nice. Dy over, or minus dy over y is equal to dx. Right? Okay? And integrate, whoops. I think I would. Integrate like that, and that gives you minus what's that? Okay. Minus log y is equal to x. I'll put plus c1. We're going to change this many times. Yeah, we're going to do the same thing. This will be log of y to the minus 1, or 1 over y, is equal to e to the x plus c1, which would be c e to the x. Okay? And then exponentiate both sides, and you have y to the minus 1 is equal to e to the cx, and then this will be 1 over y equal e to the cx. I really am not doing this right. No, c to the a. Yuck, I put that in the wrong place. I thought, this isn't right. Well, that's not right either. Okay. The c's in front. Okay. C e to the x. Now this will probably be a different c, 1 over c. Make that a c1. I don't care. So it's y is equal to c e to the minus x. Okay, now, what's that? Yeah. Okay. Okay, it's similar but not quite the same. Now, what I would want in the bottom of my heart is for these to be the same at x equal 1. There's nothing that guarantees that's going to be the case. So what I would like for that, and I don't know, how do they handle this? Do they do anything to it? Oh, they just leave it as a C, okay? They call it a C2.
Oh, so they don't even go to find out what C is?
Okay, no, they were doing exactly what I was going to say. By appealing to continuity at a point, then it would be possible to figure out what that C2 is. So, or C, what I'm calling C is. I would like for, I already know that y of 1 from this one is equal to 1 minus 1 over e. Wouldn't you say that's true?
Yeah.
Right. Okay. So I would like y of 1 to be that here too. So I would like 1 minus 1 over e to equal c e to the minus x. Right? Oh, wait, but when x equal 1. Okay, wait, sorry. c e to the minus x. I mean, minus 1, okay. All right. Which would then be 1 minus 1 over e is equal to c over e. First thing I'd do is multiply both sides by e, right? Solve for c.
Or make that 1e over e and subtract it.
What's that?
Or get the common denominator with the 1 and subtract it.
Well, that's what I was kind of doing. If you multiply both sides of the equation by a common denominator, you kind of do that.
Yeah.
So this would then be e minus 1 is equal to c. All right, so then to get continuity to work, this solution would then be this solution here would then be y is equal to e minus 1 e to the minus x. Goodness gracious. This thing is so bizarre. And Victor's here. Good deal. Double the class size. All right. Okay. We're doing example 6 on page 59. It was a differential equation with the function being a piecewise defined function. And we had a boundary value problem with it, which helped the first part. And then we wanted the y to be continuous, so that's what gave us the second part. And here's what those two functions are. The first part, this is good for 0 less than or equal to x less than or equal to 1. This is good for x greater than 1. Okay.
So, why did we put in the 1 minus, or well, what did we set equal 1 minus 1 over e equal to c e to the negative x?
Okay, why did we what?
Right there at the bottom where you set,
Here?
right?
Here?
Yes.
Okay.
Why did we use that to find out what c was? Instead of just doing it plugging in a number for x.
Okay. Well, you can't plug in x equals 0 because this function isn't defined for x equals 0. This is defined for x greater than 1.
Okay, so the reason we did that earlier is because it gave us a
Because
y
that
of
was
0
in there. It was in there. That's how you found that c. How we did this c, we wanted the two c's, we wanted the two pieces of the y, even though f was a piecewise control defined function, which was discontinuous, we wanted y to be continuous. Okay? Now, it's still piecewise defined, but we wanted it to have the same value at 1 here as it did at 1 here. Sorry. Here, this one. Okay. This is the one for here. We wanted this value to be the same at 1 as this was at 1. Okay? So that you don't have a discontinuity there. Because I believe our requirement was y had to be a continuous function. Okay? So, and besides, it's nicer if it is. And the initial condition defined which value of c we wanted to use for that, and then this one would do that. So, what we did was take this value at 1, which is y at 1 would be 1 minus e to the minus 1, or 1 minus 1 over e. Okay? And that's what we put here. That value y we want to be when this x is equal to 1. Even though that's not even defined for 1, but we wanted it to meet there. So this would be c e to the minus 1. So this is c over e. So I just rewrote this equation like that. And then since we're looking for c, I just multiplied everything on both sides by e. That wipe out this e minus 1. So then I plug that back in to this, and that would be e minus 1, e to the minus x. Now, it is a piecewise defined function, but it's now continuous at 1. So it's doing one thing up to 1, starting from that point doing something else. And the graph they show in the book, the second one in the margin, you'll see that's not a smooth transition, but it is a continuous transition. That is sort of a cusp there, not a smooth curve. You see it? Okay. So I haven't written this quite the same way they did. They wrote it more in traditional form, but I just didn't have room to do it, so I kind of strung it out like this. Okay. It says it's worthwhile to think about 9 and figure that a little bit. You are urged to read it and answer problem 48 in exercise 2.3. Knock yourself out. Okay. So now we're moving to a new kind of topic, functions defined by integrals. At the end of section 2.2, we discussed the fact that some simple continuous functions do not possess antiderivatives that are elementary functions, and the integrals of these kind of functions are called non-elementary. Boy, what a clever title. For example, you may have seen in calculus that the integral of e to the minus x squared dx and the integral of sine of x squared, not sine squared of x, but sine of x squared, are non-elementary integrals. You can't get a simple function to be that. In applied mathematics, some important functions are defined in terms of non-elementary integrals. Two such special functions are the error function and the complementary error function. Really nice. I think we have others. I'm trying to remember. Bessel function, I'm pretty sure, is a non-elementary. I think it's defined as an integral. So there's lots of things. Now you're math, you're engineering? Okay, which kind? Civil. I wouldn't be surprised if you might not run into some. It seems like mechanical and electrical might run into a little bit more, but civil may run into some functions that are only defined as integrals you can't solve. And the error function is one. Now you don't have your book, do you? So let me write this one down. Okay. Because this is a pretty famous function, the error function, ERF. That's this. Do not know why this does this. Okay. ERF of x is defined this way. 2 over the square root of pi times the integral from 0 to x e to the minus t squared dt. Now this is nothing to do with what we're doing here, but Kevin, remember when that guy came into Cal 3 yesterday? Wasn't it Cal 3?
I think it was last time we were here.
Oh, was it? Yeah, that may have been it. And he never showed back up again. Told to see me after 12:15. Never came, so maybe he got after whatever it was, but that was strange. I just happened to think it didn't happen, you know. All right. This is certainly an integral. There's no way in the world, short of numerical integration, you're going to get that to work. Okay. Now the complementary error function, ERFC of x, starts off the same, 2 over the square root of pi, and that would be from x to infinity, e to the minus t squared. Okay? Now, so these, this isn't quite the same, but it's pretty similar to your bell curve type functions. In fact, it may really be that if you, I don't know about the coefficients and all like that, but I think this is a function that basically describes your bell curve, and the 0 to x would be from here to there, and x to infinity would be everything beyond that. And that's why they call them complementary functions, because, and I think the 2 over root pi normalizes this, so the area under that is equal to 1. I'm not sure, it's been a while since I dealt with it, but it seems like that's characteristic of it. Okay? From the known result that when you combine these two together, the 2 over root pi, no, I'm sorry. No. Okay. No. All right. Okay. From the known result that this integral from 0 to infinity of e to the minus, e to the minus t squared dt is equal to 2 over root pi. Now the square root of pi over 2. Okay. That's what they say. Everybody knows that. You know. Sure, of course. So basically, the two of these things added together would be 1. And that's why I said this is a normalization thing, making everything under there 1. So the probability of something happening, no matter what the something is going to be 1, okay? It's going to happen sometime or another. If it's in the first part, it's there. The second part is outside of there. Okay? It's really a bizarre way of saying it. And that's, I didn't know that's what they were getting at too. If that is equal to that, then you can divide both sides by root pi over 2, which is multiplying both sides by 2 over root pi, and you get that the integral from 0 to infinity of e to the minus t squared dt is then equal to 1. If you divide both sides, oh, I'm sorry, 2 over root pi in front. Multiply both sides of this that equation by 2 over root pi. And this side becomes 1, the left-hand side, and this side becomes 2 over root pi times this, is equal to 1. And this is your bell curve. The probability that it's going to happen somewhere is 1. I mean, that's given, something, situation, it's got to show up somewhere, then if you cover 0 to infinity, that probability comes out to 1. So I think this is basically what they use in statistics, okay? Because of its importance in probability statistics, applied partial differential equation, the error function been extensively tabulated, and the error function of 0 is 0 is one obvious function value. The error function of x can also be found using computer algebra system. Okay. And I'm not sure I really want to do this, but let's do it. Give it a shot, and if it gets too weird, we'll hang it up. Okay. Solve the initial value sorry. Solve the initial value problem, dy dx minus 2xy equal to, with the initial value y of 0 is equal to 1. The pen is so stinking slow. Okay. Y0 is 1. All right. Now, how would you proceed on this?
You're not going to separate the variables.
Not going to separate those variables. No way. Okay. What's that?
We're going to take a different approach.
Yeah. It is a linear differential equation. That's sort of the key here. That's going to be your integrating factor is what we call it. Yeah. Okay. Now, what do you identify first? Okay, and what is your P? P of X. The P of X, that's a P. P of X is equal to minus 2X. You got it. Okay? And then what's the next thing you do with that? You integrate negative 2x dx. Right? Okay? And what does that give you? Second?
No, it gives you
And how,
half x squared.
right. Okay? We don't do a thing. So that loses the 2, so you got a minus x squared. Okay? So there's your...
You raise that to e, right?
Yes. So then you'll have e to the minus x squared. That's looking sort of familiar, isn't it? Okay? Now, multiply everything on both sides by that. So that gives you e to the minus x squared dy dx minus 2xy e to the minus x squared is equal to 2e to the minus x squared. Okay. Now, this side had better be a perfect differential, right? Yeah. Here's one part. There's your y and your dy. Right. And the other part is e to, yeah. So here's your function here. So this is the derivative of, differential of, which way do I want to write that? I guess it really matters. E to the minus x squared y. Probably I wanted to write it in front. But anyway, we're okay. Is equal to 2e to the minus x squared dx. Right? I wrote it in differential form at the same time. Okay, and when you take integral of that, you just get e to the minus x squared. I'm going to put the y in front. Okay. Wishy-washy on that. And this is going to be 2 times the integral of e to the minus x squared dx. Okay? And that's the error function of x, right?
That's it.
Well, a little bit of an issue here in that you need a constant in here somewhere that we got initial condition, so we'll just leave that as, we'll say plus c. Okay. Now, Notice above there they said error function of 0 is 0. Okay? And I've already erased all the stuff that said what that was. The 2 over root pi and all like this really don't come into play directly here, because when you put a 0 in there, you get a 0. So, and y is 1. When x is 0. So that'd be x is, so that's going to be 1. So it looks like 1's equal to c. It seems a lot too simple, but it does seem like it pans out that way. Okay. Did I introduce it too soon or too late?
Just took the integral, so
What's that?
I said you just took the integral, so it couldn't be too late.
Well,
You wanted to do it off that first one.
Right.
You don't, you don't do that.
um,
The P of X, whatever.
Yeah.
Unless it was going to be y c e to the negative x squared.
okay. So what we did, we were down to that point exactly like they were with no sweat. And then what they do is multiply both sides by e to the x squared from here. You see, you've got one here. If you're trying to isolate the y, okay. They do a couple of things here that I knew when I was writing this that it was going to come to this at some point. This x and the one in the integral are not quite the same thing, okay? You really need to change. But what they do is put the x as 0 to x here, and then make that a t. Now that's sort of a dummy variable anyway. And I was trying to read to see if they had any justifiable reason for doing that, and they just sort of skim right past it almost. Okay. We got the same thing they did. C is equal to 1. Okay. Hence, the solution of the problem is.
So how did you get C is equal to 1? You just plugged in
Yeah, y when x equals 0, y is equal to 1. So we're going to put a 0 in here, a 1 in here,
and that's all that's left.
and this is 1. E to the 0 is 1. This is 1. And this thing, the error function evaluated at 0 is 0. They told us that, so then the 1 is equal to c. So c is equal to 1. They did it slightly differently, but got the same thing. So basically, I just need more room. So I'm trying to think where the best place to erase this is. Let's get rid of most of this. But I don't want to get rid of too much. Okay. think we've done all this. I think I'll just hang on to that last piece. I hope I didn't destroy anything we need. Okay. But like I'm saying, this x here shouldn't be x, it should be t. Okay? They just do this. They put that as x and put this as t. And it is a legal thing to, well, a legal thing to do, but it's just not explained very well. Okay? Number one, and that's probably where the differential stuff is a little on the sloppy side too. That gives you a function of x on both sides. So what we're going to do at this point is this will be y. I'm going to multiply both sides by e to the x squared. Okay? Yeah. Okay. Of this also. In fact, I should have done the whole thing. To me, it's just a little bit nicer to do it that way. Okay. Everything by that. Okay. Okay. So what that gives us is y, because this times that goes to 1, is equal to 2 e to the minus x squared. No, e to the x squared. I'll do it that way. Make that a plus. Okay. And this is the error function. That is the error function. Okay. Well, almost the error function. What we need is we need a 2 over pi in front. Okay. Let's leave it like this for right now. So this, and we'll leave this here. 0 to x e to the minus t squared dt plus c e to the x squared. Okay, because we multiplied everything on both sides by that. Okay. Now we're going to use this thing again. Okay. When x is equal to 0, y is equal to 1. So 1 is equal to 2. When x equals 0, that's 0. Wait. We've already done that. I'm sorry. Where my brain is, I don't know. This is a 1. Okay. We've already done that part. Don't need to do it again. Okay, so that's our equation. But recognizing that 2 over root pi times this integral 0 to x e to the minus t squared dt is equal to the error function, ERF of x, right? That was from, is it top of the page? Bottom of the previous page. Okay? That is the error function. Well, how could we get that to be? Well, we could, let's take this 2 from here and move it here. Multiply and divide by root pi. Okay. Now this part is the error function, ERF of x. So now we have y is equal to, we move that over there, e to the x squared root pi e to the x squared ERF of x, because that now is that, plus e to the x squared. Okay.
So what you did was
Wrong page. Yeah. We saw this was awfully close to being the error function. That's the error function. So we already had a 2 there. All we needed was a root pi in the denominator. So I multiplied by root pi in the numerator and denominator. That made this the error function. And then combining things together, root pi e to the x squared becomes error function of x plus e to the x squared, which I really want to factor out the e to the x squared and have root pi the error function plus 1. They don't do that, but you could have. Yes, they did. They did do that, ultimately. They had this, and they wrote it the other way. Okay. E to the x squared times, I think they put the 1 in front, 1 plus root pi ERF of x. Okay. Now, as they said before, the error function has been tabulated forever, okay? It's kind of like back before calculators, when you had sines and cosines, you looked them up in a table to see values that gave you as close as you ever wanted to get, 4, 5, 6 decimal points, and you looked up at a table. Same thing with exponentials and logs and things that you couldn't calculate, the transcendental functions. Now we got calculators. Well, you either got computers or calculators, so it'll do error function. You're a big fancy one. I wouldn't be surprised if somewhere on there you don't have an error function on it that you could plug in anything you wanted to and get it. Okay? And that is the answer. Okay? Now, the graph of this solution on the interval minus infinity to infinity, shown in the dark blue. This is the one where y is equal to 0 is equal to 1. Y of 0 is equal to 1. That's the dark blue line here. And you,
EFF.
it's ERF. I don't know what EFF is.
I don't see the ERF, just EFF.
Okay. I don't know what that one is. Maybe it is it. I don't know. See what that of 0 is. Probably will be 0. That doesn't prove anything, but if it's not 0, then it's not.
Error argument.
Okay, yeah. So you can't. So EFF doesn't work. All right. There is the function here, solution curve. This is your y, and for different values of c, you go further to the left. This is at c is equal to 1. I don't know if there's a negative c's or positive c's. You would be this way, and the other way heads back in a different path. But they use computer algebra system. Now they have a little blurb here, use of computers. We don't have these programs, so we're going to leave them alone. The remarks here are pretty good. In many ways, review or summary of what the chapter has said, but they also expand a little bit, okay? We've mentioned homogeneous and non-homogeneous. Actually, the previous example, one of those things was homogeneous and one was non-homogeneous. When it was equal to 1 for a certain range and 0 for the other. The 0 was a homogeneous, the other was not. And we made them connect there. They also say occasionally a first order differential equation is not linear in one variable, but is linear in the other variable. For example, and they do give this one, goodness. I'm not going to mess with that. It's sort of an interesting kind of a topic. It's talking about reversing the derivatives. And that is maybe something we ought to do. I think it's beyond what mostly we will ever be doing here, but all right. I can't believe they're giving us this now, but it is. Here's a dy dx is equal to 1 over x plus y squared. Now, first glance there, non-linear, okay? But what they're proposing here is to make it a linear function by dealing with the reciprocal. And here again, mathematicians probably crawl the walls on this. This is saying, well, then you could do dx dy is equal to x plus y squared, couldn't you? Yeah, I guess you sort of could. And then, yeah, it seems like it. And now you just changed around your independence and dependent variables, big time. And then you could subtract the x from both sides, because that should be over here. No, yeah, that's right. So dy dx, I'm sorry, dx dy minus x is equal to y squared. There's your function of y. Yeah. Well, your integrating coefficient here is minus 1. Yeah. And, go from here and solve it that way. I know. It sort of makes your skin crawl if you're a pure mathematician, which obviously you are becoming one. Okay. But now your x is your dependent variable and your y is your independent variable. Now, mathematician, what's that? It really did, right. Mathematicians, this is number 3 here under these remarks. Mathematicians have adopted their own certain words from engineering, which they found appropriately descriptive. The word transient is one of those. Input, output usually pops up. Input or driving function, output or response function. And then the term special functions mentioned in conjunction with the error function also applies to the sine integral function, which is not the same as sine, but sine integral function, and then the Fresnel sine integral function. And they're introduced in problems in this one, which leads to, the only reason I'm mentioning them here, potential paper topics. Okay? Who was Fresnel? How did he come up with this? What are uses for this? What is uses of these, including the error function, Fresnel function, what were the others I named? I can't think of the name now. But there's several of these functions. Any of those would be paper topic, especially for how are they used, and maybe are they used in my field? How do I need to do this? So anyway, yes. All right. Exercise set 2.3. Any of the odds 1 through 23.
This is the one with weird numbers.
Yeah, and I think all those should be back here. I didn't check. Let me see. 2.3. I'll put a piece of paper here. I don't have that. Okay. 2.3, 1 through 23. Yeah, all those are back there. Any of the odds 25 to 35. I think all those should be there. Look like they are. Either 37 or 39. Both of those are there. Those are the piecewise defined, so that's one like we did today. And then either 41 or 43, or both. 43 is the error function. Okay? Then there's some discussion problems, if you can read those and view, see if there's anything that really strikes your fancy there. I think one of those was the Fresnel, but I don't see it now. Sorry.
Matrices and derivatives and stuff.
What's that?
I was turning back to find the homework and
Yeah.
this little matrices section where there's integrals and derivatives and stuff.
Right.
Matrices.
There's a problem on heart pacemaker, which if it doesn't sound like either one of you might be going into medical type. Oh no, 56. There's the Fresnel. Would be a maybe a decent one to look at. Anyone listening at home, if that's what your goal is, you might be interested in that as a differential equation. Then there's some computer lab assignments, which obviously we don't have things. The sine integral function, which is called SI of x, capital S, little I of x, is the integral of sine t over t dt, where the integrand is defined to be 1 at t is equal to 0, even though it seems to be indeterminate there, but you define it that way. And then the Fresnel sine integral problem is slightly different, but it's somewhat similar. So if you're interested in those, following up on those, and I can't, for the life of me, I can't name the other function that I mentioned earlier that I said was one of these integral defined function. I can't even think of it now. You'll run into them if you need them. So let's move on to exact equations. All right. Little bit of background, I guess. Here is a simple first order equation. Y dx plus x dy is equal to 0. Okay? That's separable. Okay? Subtract x dy from both sides. I would subtract y dx from both sides. And then divide by y, divide by x, and you have dy over y is equal to minus dx over x, and go on and work from there. Okay? But rather than having to go through that, an alternative manner, by recognizing that the expression on the left-hand side that's not 0, is a differential function, okay? Kind of like what we were doing when we did the integrating factor. Wait a minute. Here's a x and a dx. Here's a y and a dy. So that looks like a product rule, kind of, doesn't it? Of derivative of xy. Okay? Wouldn't that be derivative of a product be x and dy plus y times dx? Yeah, same thing. Okay? And what you're saying here is the derivative of that product is 0. That means that product is always a constant. So this is saying xy is equal to some constant. Okay? In other words, y is equal to some constant over x. Okay? Now, in this section, we examine some first-order equations in differential form, and these will be more like this. M of some function of x and y, let me make sure I get it right, yeah, dx, plus some other function n as a function of x and y, dy, and is this always, yeah, always equal to 0, or at least start with equal to 0, okay? Now, what we did here, we saw that happened to be a perfect product rule. Well, for this to be the case, that would mean require m of xy basically to be equivalent to y, n of xy be at x, which is a bit of a stretch here, but there is a test you can do. We can determine whether this is a differential function of alpha of xy. Okay? If the answer is yes, we can construct f by partial integration. Okay? Partial integration. Is that a new term? Okay. Here's where we'll start. Let's just assume we've got some variable z we haven't had before is some function of both x and y. Okay? Wait, y'all haven't had partial derivatives, have you?
No.
You haven't, have you? Have you had Cal 3?
Cal 3 as well.
No, you're in Cal 3 as well. Ah,
I thought
boy.
you said we wouldn't run into these.
Yeah, well, we might just skip this section. Well, the part that depends on this.
How long would it take you to give us a briefing in? Probably more than a minute.
No, it's not bad. Really, partials are pretty straightforward. But I think, except for at the very, no.
But will we use
That is your criterion for exact differential. You will be using that. Okay.
Will we use this later on as well?
Yeah, you'll definitely, well, let's see. This, I guess, is why this is Cal 3 is a prerequisite. I had forgotten about this. Okay. All right. Let me,
It's past 10:45, right?
well, what time is it now?
We have
5 minutes. Okay, let's do a very quick, let's see, do they have anything in the back that would be helpful? If they have a little blurb on partials, derivatives. A gamma function was another one of these that's defined as I don't know if that's, I doubt if that's the one I said, but that, as soon as I saw that. And matrices, I know you're itching to get there. And then
Itching to get where?
matrices, Laplace transform, and then answers. I think, no, that's it. Okay,
Yeah.
let me give you a quick and dirty on partials. All right. Let's do z is equal to alpha of xy. Okay. What this means is you have two independent variables, one dependent variable. Okay. Now, you can't do derivatives with that because a derivative with respect to one independent variable. So the partials, and let's just make up a function. Z is equal to, give me some function that depends on both x's and y's. You put them together however you want to. X squared plus y squared. That will be a real nice simple one to do. Okay. Now, what you can do the derivative of z with respect to x, because that's an independent variable. But when you're doing that, you hold y as a constant. Okay? So we call that the partial of z with respect to x would be what? 2x. But you're counting y as a constant, so that's going to be a 0. Okay? But the partial of z with respect to y would be 2y. You got it. That's all you do. Okay? That's what we mean by partial derivatives. You got more than one independent variable.
So you just kind of do the cheating type thing of saying one variable is a constant and the other isn't. You derive them individually.
Yes,
and
exactly.
then you get two answers.
Right.
All right. So can we do a more in-depth one?
Sure. You make it up and we'll do it.
Let's see.
You want us to keep it z?
Yeah, z equals x
log of y. Okay, perfectly legal. Partial of z, and this crooked looking d symbol, that's your partial. Partial of z with respect to, which one you want to do first? X? That would be what?
Well, that would be, it would just be fine.
Yeah, because you count y as a constant. That's some constant times x. Derivative of that is the constant. Okay? The other, y is a constant. Derivative of a constant is 0. Okay? Partial of z with respect to y would be x
Plus
1 over y. You got it. That's it.
Is there any of these where it gets kind of hairy? I mean, I'm sure there is, but
Yeah.
anything to watch out for specifically?
I can't think of any that would be especially rotten. When you were trying to make up one, I was wanting you to say, well, throw a sine or a cosine in there, and you could do that, and it's still, it's you just do it.
Motions
You know.
and all that, it's just, you just
Yeah.
treat one is a constant, one is a variable.
Right. Yeah.
So,
When you're taking the partial with respect to one variable, all the other variables are treated as constant. You just focus on the one, and then you do a different one with this. It just winds up you have a variety of these. Okay. So that's what we mean by that then.
that's not too bad.
So if you go back to our first statement there, z is equal to f of x, y. Now, and here's where they mix them a little bit. dz, that's derivative of z, that's a real d there, is equal to partial of f with, because that's what you're doing, partial of f with respect to x times a dx, and that's a d, plus the partial of f with respect to y dy. So that's a
Is that
d
F
there.
or a T?
That's f. Yeah, that's what I said. If z is some function of f and y, x and y.
I'll just make sure.
Yeah. So whatever that was, partial of that function with respect to that dx. So this is how you get a multiple independent variable, single dependent variable into what we call differential form.
So the actual d's are with dz and then in the denominators, right? Or are those the d's, are those the funny d's in the
Yeah,
denominator?
these are the partials.
Okay, those are
That
both
is
partials.
actual differential.
So the differentials are not in fractions and then the partials are in fractions in this problem.
And this,
Yeah,
the way
I
I've
was just
written
making
that.
sure I have it.
Yeah,
Understand
he's
what-
making fun of my writing, is
No,
what
I'm
he's
not.
doing. Yes, I understand. I'm hurt, but I can handle it. Okay.
Yeah, two different D's.
Yeah, the straight D's are derivatives, are differentials, and the curly ones are partial derivatives.
I almost write them, you know that funny L they have? Almost
Yeah.
write it like that backwards with a curl in each letter.
Yeah,
And just make it look really weird so I know it's different.
right.
And it is 10:45.
It is. Okay, we'll stop there and pick up.
We got shoe ahead the rest of the class. Count three.
Okay. We will
And
do.
if that's all we're missing from count three to do that, I think we should be fine.
I think so. It's all I can recall. I had forgotten about this one section here.
You don't just teach this class a whole lot though, do you?
What's that?
Differential equations, you don't teach this.
No, it was more than a year ago I taught it to, well, wait, Brittany Terry took it using my,
Old video.
oh, I didn't even teach it that time, she just used the old ones. And that was from when I taught it to John, goodness, I can't think of his last name now, and he was the only one in the class,
So this is the biggest difference in equations.
oh, ever, okay, yeah, 5, but only 2 typically show, okay. Yeah, this is the most we've ever had. All right, good deal.
See
Have a
you
good
count
weekend.
three for some-
Oh, let's see. Are there any homework exercises here in this section? I'd say start doing some of. Oh no, we didn't get far enough. Don't
All we
worry
did
about
was
that. Yeah, definition of what it is. Okay, so that gives me. Yeah, let me stop that.